models over ring. And we started discussing the tensor product of, this is definition of tensor product, and you will have it in handouts as well. The main property of tensor product is its homological property, which is how it is related to exactness. It is right exact. So if you have an exact sequence, embedding doesn't go to embedding, but surjection goes to surjection. This is something we proved last time by some more or less conceptual argument, which is also in handouts, but you can do that as an try to do that as an exercise without any conceptual. Maybe it will work, I'm not sure. I think it should work. Just you sit and try to prove it, write formulas, and then you probably would get the exactness. And there is the important consequence which you might have, namely that what happens if you take a model and multiply it by a quotient of a ring, by an ideal, and this is the same as you take this model and take its quotient by IM. I is elements of ideal and multiply it by the elements in your model. Have any questions for that? This was last time. Okay, good. Now tensor product of rings is if you have two rings, you just take their tensor product as models. So if you have A, B rings, C to A, C to B, and C also ring. Homomorphisms, ring homomorphisms. Then A over C with B is also a ring. So I take the tensor product as models, C models, and define multiplication on this tensor product. Okay, it was, again, I didn't write reminder, but it is a reminder. So there was an example which we discussed sort of in detail with polynomials. So product of polynomials is polynomials. Yeah, and also what you can do is you can multiply from this. This implies that if you take A and multiply it over C with C quotient by I, this would give you A quotient by IA. IA means that you take image of I in A and generate an ideal by this image. This just immediately follows from this. So I'm repeating what was last time with tensor product. Now let's do associativity. This is something we started discussing but didn't finish. So if you have A, B, D rings, C and C prime also rings, and then you have homomorphisms like that. Homomorphism. I'm giving you the associativity in the most general format. Of course, you can work with like C is equal C prime and weaken this assumption somehow, but anyway. So you can take A tensor over C with B, multiply it. So B is C model and C prime model. If you do this tensor product, you still have a homomorphism from C to B, and this gives you a homomorphism from C to B tensor A because one tensor B is contained there. So this is, there's a homomorphism from one tensor B to here, so this is a homomorphism from B to here, and then this is a homomorphism from C to here. It makes sense. And I claim that this is the same as A tensor over C, B tensor C prime with D. This kind of associativity. This is sort of standard, and as all associativity with tensor product is proven by universal property of tensor product, which I think it was previous slide. Yeah. So tensor product is by definition something which represents bilinear maps. So if you have a bilinear map, it is the same as a map from tensor product. Good. So now, by definition, homomorphisms from, and here you don't need that to be rings. It can be models. It doesn't matter. So I stated for rings because we need it for rings. But in fact, this is a statement about models. It's not. But then you have to B, and C prime model. And so let's stick with rings. So you take homomorphism from this tensor product, A tensor B tensor C prime D to M. This is, so this is, since the last product was C prime, it is the same as bilinear over C prime. So this is bilinear over C prime from A tensor B D to M. Okay, but what is maps from A tensor B? What is bilinear map? I mean, what is linear map from A tensor B? This is the same as bilinear map from A and B. So this is the same as bilinear over C prime. Then you take bilinear over C, A, B, D times D times So the linear maps from M the same. So here we have also map to M. Well, it's like bilinear from A, B, and D to M. So here we have, let's write it like just, okay, let's write it like that. You have three linear map, linear in all three arguments, A, B, D to M. So here we have, this is C prime model, so this should be considered over C prime. This should be considered over C. Anyway, the idea is that bilinear maps from this is the same as trilinear maps, and trilinear maps are associative just because it doesn't matter in which order you take. So you can write it like is written here, just explicitly check that. So universal property means that these homomorphisms are the same as homomorphisms which are linear in first, second, and third argument, and then it doesn't matter in which order you take.
And you decided to use here that the direct sum is associative.
I didn't actually use direct sum, it's a product. Theoretic product, yeah, and it is associative. Thank you, yes, this is important. It's associative just for obvious reasons. Okay. This is sometimes used, and I will use it today a couple of times. This is why I wanted to state it explicitly. Now we have, again, the notion of a spectrum, something we had already. So if you have a finitely generated ring, then A is polynomial, x1 polynomial ring, xn, quotient by ideal without nilpotence. Or it doesn't matter. If it has nilpotence, just take a quotient by nilpotence. Then this ideal has common zeros. Vi is common zeros of I. This is subset, affine subset in Cn. So Vi is denoted by spectrum of A. So this is definition. Of course, the set depends on the choice of generators, but as we have seen several times, Hilbert-Nullstellensatz essentially implies that as affine set, that doesn't matter. That's by equivalence of categories, affine varieties, and finally generated rings without nilpotence. So let's assume it has no nilpotence, doesn't matter. Nilpotence. So this is called also reduced. Doesn't matter because if it has nilpotence, the same argument just brings you that this is it just depends only on the quotient of A by its nil radical. Okay, so one of the applications of tensor product is that you can now write explicitly the preimage of algebraic morphism. So let's have f from x to y, a morphism of affine varieties, which is the same as homomorphism, ring homomorphism from regular rings on y to regular functions on x. This is again Hilbert-Nullstellensatz. We have discussed that a lot.
What is saying? So you got a map between affine varieties.
Yeah. So this is the same as map from corresponding finely generated rings. We proved that there is an equivalence between morphisms of affine varieties, which is polynomial maps, and homomorphisms of the corresponding rings. This is essentially Hilbert-Nullstellensatz. They're equivalent. If you work with schemes, you don't even need them to be reduced, but we just assume that the rings are reduced. Okay, now I can state you this proposition. So you have f from x to y, a morphism of algebraic affine varieties. You have the corresponding, you have a point y in x, y, in the big Y. This is a point or the same as maximal ideal. We proved that the points, this is again Hilbert-Nullstellensatz, ports are the same as maximal ideals. Point in Y. Then you have the corresponding maximal ideal, my. This is the maximal ideal in OY, maximal ideal. Then we have f minus 1 of y. This is an affine variety. I think we have discussed it last time, that why it is affine variety, because f is a polynomial map and y has coordinates. So the preimage of the point y is just you take equations for x and you add equation that f of a point has these coordinates. This is n extra equations, where n is number of coordinates on y. Okay, now we can take this is algebraic, so it's affine variety again. And I want to describe it in terms of the corresponding rings. So I write Ri. Why it is R1, Ri? Okay. So yeah, of course, R1, because we take R quotient by nil radical, where R is OX multiplied over OY by OY quotient by maximal ideal. Yes?
We don't need nilpotence.
There could be nilpotence. Yeah, so you have to take the quotient. Yeah, no. There is no nilpotence here and here, but there could be nilpotence in the tensor product. This is what happens. In fact, there's an exercise next slide. Do this, construct an example where it has nilpotence. I'm not going to force you to do it now, but you have to think about that at home. Okay, then spectrum of R1 is F minus 1 of Y. So you can use tensor product to describe preimage of a point. So let's prove this. No, the proof is not very hard. So the idea is that you just, so first of all, we know what is this. So R is OX. This is something I have erased, but we had it. So if you have A multiplied by C over C with C over I, this is the same as A over IA. This is what we used. We use it now. This follows from tensor product, the properties of tensor product models. So R is OX quotient by I times MY times OX. So what is MY? This is functions which vanish in, this is functions which are divisible by functions on Y which vanish in point Y. So all functions like alpha inside my times OX vanish in f minus 1 of y, right? Because this is functions from y vanishing in this point y. You take their preimage, they vanish in the preimage of this point. So this means that yeah, and by so v, let's denote this by I. This is the ideal. So vi contains f minus 1 of y. Because all functions which vanish, which belong to this ideal, they vanish here. On the other hand, if you have x which doesn't belong to f minus 1 of y, then f of x, there exists alpha in Oy, function on y, big Y, such that alpha of f of x is non-zero. We take preimage of alpha, then f star of alpha doesn't vanish in so we want to show that x, there is a function which belongs to this, and alpha belongs to the maximal ideal of x, so of y. So this is a function which vanishes in y and doesn't vanishes in that. These two distinct points, and by Hilbert-Nullstellensatz, if you have two distinct points, you have always polynomial function. Well, it's not. I mean, you can take coordinate functions for that. You don't need Hilbert-Nullstellensatz even. Anyway, you have such a function. Then f star of alpha, it belongs to this ideal I, but does not vanish. Not vanish in x, in this small x. This means that Vi is precisely f minus 1 of y. Because a point, all points in f minus 1 of y, they are common zeros of this ideal, and then all other points are not common zeros of this ideal. I mean, are not common zeros of this ideal. So step 2. Now we have Vi is precisely f minus 1 of y. And by Hilbert-Nullstellensatz, this implies that the quotient of, so you take or x quotient by y, and then quotiented by nil radical. And this is the same as O f minus 1 of y. Because, we're in trouble. Well, what is the canonical way of dealing with this? Do you know? I don't have Windows. But can we just do Control-Delete? Won't work? Won't help? Too bad. OK. So what I wanted to tell you. But, you know, the Windows update can take several hours. Yeah, yeah. And people just sit and wait? Yeah. Terrible. Windows is evil. OK, so let me finish with this. Now, everything?
Yeah.
Not that it helps that much. OK, thank you very much. Now let me do do a summary of what we have done. So we started with a point. We took its preimage. We interpreted this preimage as an algebraic subset. We took its ideal, and we proved that the ideal of this subset is just well, it's the ideal of the ring R1, because R1 is obtained from R by taking quotient by nil radical, and so on. This is not hard. So now let's continue the same way. I will give you another interpretation of tensor product. What happens if you take tensor product of two rings over C? So let A and B finally generated rings over C, and we take A times B over C, over numbers. And we again are interested in spectrum of this ring. So what algebraic variety corresponds to tensor product of this ring? And it is spectrum of A times, just times, as said theoretically, spectrum of B. At some point, so it's a theorem. At some point, we actually proved that if you have two algebraic varieties, their product is again an algebraic variety. It's not hard, and you just, how you prove that? You take A is a polynomial ring, x1 dot xn, quotient by I. You take B, C of t1 dot tm, quotient by j. And then we have to apply this twice to both sides of this tensor product, and to obtain that A times B over C is the same as C of t1 dot t, oh, sorry, x1 dot xn, tensor product with C of t1 dot tm, and when we take the quotient by I times 1 plus j, yes, 1 times j. How you do that? Well, you just, we know how tensor product commutes with taking a quotient by an ideal. So this is a quotient by ideal, this is a quotient by ideal, like R1 times by I, you multiply by R2 times quotient by J. This is the same as R1 times R2 quotient by J. And this quotient by I times 1. I times 1, this is an ideal and the tensor product generated by I. And then you apply this again, you obtain that this is R1 times R2, quotient by I times 1 plus J times, by 1 times J. This is just the same result applied to two sides of the equation. Sorry. But how now? How it is possible to extend it to the whole? Oh, thank you very much. Yeah. Oh, no. Okay. It's still there's some. No, it's bad. No. I don't like this. Is there no way to make it like it was? can just use Firefox. But there is some way to do it in this stupid Chrome as well. Good. Okay. So to do it properly, you actually need to use this lemma, but it's just trivial. And then if you have A times B quotient by 1 times I, this is the same, where I is an ideal in B. This is the same as A times B quotient by I. This is more or less the statement plus associativity of the tensor product. This is almost immediate. Then this gives you this. This gives you this. Okay, so this was step 1. Now, it's slightly easier to prove not what I did here, but take the quotient by the nil radical. I will prove that there is no nil radical, but it will be next couple of slides. So I would start with proving this statement up to nil radical here. Well, it doesn't matter because and spectrum makes sense for things which have nil radical, but you have to work slightly more. So how you prove this? You just again use the Hilbert-Nullstellensatz. So the ideal, we take I plus 1 plus j, I tensor 1 plus 1 tensor j. This is an ideal in the polynomial ring C of t, x1 dot xn, t1 dot tm. I remind you that the tensor product of two polynomial rings is just polynomial rings of these variables. So this is a product of these two polynomial rings. This is the ideal, and I claim that common zeros of this ideal are the same as Vi times Cm. Vi times Vj, sorry. So first, if something vanishes in Vi and Vj, it clearly, if something belongs to this plus this, it clearly vanishes there, right? I mean, if something belongs to I, it vanishes in Vi times whatever. If it belongs to J, it vanishes here. On the other hand, if, so what we need, then by Hilbert-Nullstellensatz, it would follow that spectrum, if we prove this, spectrum of A times B is the same as spectrum of A times spectrum of B. So again, what we need to, if we want to study the ring, we study the ideals. If we can prove that, so we know that this ideal defines this ring. we need to show that if we want to show that the spectrum of this ring is a product of these two spectra, we need to prove that the common zeros of this ideal are precisely this product. So what we know is that the common zeros, v of I times 1 plus j times y times 1 times j, these common zeros of this ideal contains vi times vj. This we know. This we just discussed. If something belongs to vi times vj, all elements of these two ideals vanish in that point. Conversely, suppose you have something, a point which doesn't belong here. Then you take an element which, so we need to prove the converse inclusion. Converse inclusion. Suppose you have x, y, a point in Cn times Cm, which doesn't belong, xy doesn't belong to vi times vj. We need to show that xy doesn't belong to the v of this ideal. I times 1 plus j times 1. Oh, 1 times j. How you prove that? Well, this means that either x doesn't belong to vi or y doesn't belong to vj. Suppose that x doesn't belong to vi. Then there exists a function f which belongs to vi such that f of x is non-zero. So this function, of course, f doesn't belong to I. That is, f of x is non-zero, if this is true. It's again Hilbert-Nullstellensatz or just definition. Then, okay, we take f times 1. It belongs to this ideal, but it doesn't vanish here. Does not vanish in vi times vj. And that's proof. We're done. Because we proved that all points which belong to the product belong to common zeros, and all points which don't belong to the product don't belong to common zeros of this ideal. This means that this ideal indeed defines the product of these two varieties, but this is ideal, as we just shown, this is an ideal of tensor product of the rings. Okay, do you have questions about this? This is almost tautology. You don't need to do much, but yeah. Also, I will prove that tensor product of reduced rings is reduced. This is only for over C. Generally, it's false. Even over C, it's not obvious, and you need Hilbert-Nullstellensatz, in fact, to prove that. Okay. Yeah, but let me just leave it for you to read this as an exercise, because there's nothing to do, and we don't use it anyway. So I will leave it for you as an exercise to save time and energy. The proof that, let me write this as an exercise. You can prove it yourself, following the same ideas, or look in my notes. So exercise. you have A, B, finitely generated rings over C, no, reduced, no nilpotence. Then A times B over C is reduced. The idea is, again, you take intersection of all prime ideals, which gives you nil radical, and then you check that intersection. You have enough maximal ideals coming from A and from B already, so that this intersection has to be 0. There was one more exercise, I think, somewhere. Yeah. In fact, if it's not over C, you can't have nilpotence. This is another exercise. So exercise, it's actually harder than this one. If you have A and B over C reduced, but C is not in complex numbers, it's just some ring, then find example when A times over C B quotient by maximal ideal is non-reduced, contains nilpotent for M maximal ideal in B. So generally, tensor product can behave strangely, but fortunately for products over C, it doesn't happen. Okay. I am now going to give you interpretation for all tensor product. Let me state it, and then you will have a break. So there are some lemmas, and we don't really need them yet. So this is what I am going to use. So this makes sense in pretty much any category, like category of affine varieties, topological spaces. And in fact, you can do everything very categorially. So definition. But here it is for algebraic varieties. Yes, so let's F, how it's denoted, Px and Py, x to m Px and y to m Py, morphisms. Then x over m by y is a set of all points x and y in the product, such that Px of x is equal to Py of y. So this is small x, small y. Again, this is an algebraic variety, for the following reason, that if you have a pi, I mean, this is an algebraic equation. These are two polynomial maps. You have 2 points. You apply polynomials, and you assume that this applications of these 2 polynomials is equal. This is algebraic condition. It's preimage of diagonal. Yeah. Okay, this is called a fiber product. Okay, and now the main result for this today's lecture is that tensor product is fiber product. So if you have so there's 2 lemmas which were on previous slide. I will discuss this after the break. So, but the claim is clear without these lemmas. If you have this x to pi x to m, y to by pi x to m, algebraic, affine morphisms, algebraic morphism for affine maps, affine varieties. Then the spectrum of x of OX tensor product over OM with OY. You see they're both mapped to M. This means that the functions on M are mapped to OX and OY. This is the same as X product over M with Y. Okay, let's have a break, 5 minutes. So it's, we shall resume at 28 minutes. And there are a couple of things I want to distribute. First, this home assignment 6. It's for you to study the tensor product. It's again, there is no grading. It's for discussion. If M is C, just trivial, I mean, the zero-dimensional the ring of one point, then this claim is a special case of the theorem which I proved. So let's prove this result as well. There are a couple of claims we have to use. So first is what do we do with preimages? It's like we had with the point, but slightly stronger, and the result is very similar. And the proof is precisely the same. This is again up to nil radical, of course. So you have claim 2. You have x goes to y, affine morphism. So it's affine varieties with polynomial map. You have z inside y as a variety. Z inside y is a variety. Then we take tensor product again by, so this is a variety and it has an ideal IZ. It's ideal. So IZ is ideal of functions in O y which vanishes in Z. Then we take O x multiplied by over OY with OY by IZ. So this is, we'll multiply it by OZ, in fact. And we take its quotient by nil radical, all nilpotent elements. We denote it by R1. Then spectrum of R1 is equal to f minus 1 of z. If this is a point, this is precisely what we had before. But you can do it more generally, and the proof is the same. Okay, we are interested in all functions which vanish in f minus 1 of z. This is the ideal of this subvariety. So clearly, if you have a function in this ideal, IZ and plus nil radical, this function clearly vanishes in this subset. And if you have a point of this subset of x, which doesn't project to z, you have a function which belongs to the ideal of z, but doesn't vanish in this point. The preimage of this function doesn't vanish in this preimage. This is the same argument. So common zeros of 1 times of I z times Ox is the same as points in f minus 1 of z. So this is the ideal of this tensor product. And it's the corresponding, it's the set of common zeros of the elements of this ideal is precisely the preimage. Should I repeat, or is it clear? So for who wants me to repeat this? What I did now is that essentially tautology. I did not do anything non-trivial. I just indicated what ideal defines this ring, R1, what is its common zeros, and checked that this common zeros is precisely f minus 1 of z. And again, I use the same argument as previously, as when this is a point. This is precisely the same statement. OK. Now, about diagonal. We are interested. So what is diagonal? Diagonal is you have an, what should I erase? Okay, this we need, so let's erase this. We have a map from m to square to m times m, which is clearly algebraic. M to m times m. X goes to x. OK, algebraic is good, but we didn't actually prove that the image of algebraic is algebraic. It's not entirely true. It's sort of complicated. In the end, what you can prove is that the image of algebraic map is a complement of algebraic set. So it's what is called constructible set. It's not algebraic set. So, but the good thing is that this is still, you can still define this by an, so this is diagonal map, diagonal. And its image is also called diagonal. Its image also called diagonal. And then it is defined by an equation, x, y is equal to yx. So you have 2 points in n times m. So this belongs to m times m. You can permute these points, and if it's the same pair, this is diagonal, and this equation is clearly algebraic. So diagonal is algebraically defined. So algebraic subset. Am I clear? Good. Now lemma. If I ideal of x inside Cn, then so we are interested what is the ideal of diagonal in this product. I mean, and the answer is that it is generated by pairs. Yeah, we don't need it actually in Cn. So we don't need this actually. So what we need is that we consider x time diagonal inside x times x, and it's generated. Its ideal is generated by r times 1 minus 1 times r. By these elements where r for all r inside Ox. So it's sort of clear that if you have such an element, it vanishes on diagonal, because it vanishes on x. So what we need is to prove converse. So let's prove converse. It's not very hard. So again, what we need is first, if you have a point which is not in diagonal, then clearly okay, so what the first this is something I promised you not to use, but it is somehow used here. So x times x is, OX times OX is a reduced string. Well, probably we don't need it. But what we need to show is that, that V of this, the common zeros of this ideal, let's call this ideal I, is the same as diagonal. This by Nullstellensatz. Well, up to, you have to check that it has no nilpotence, but it's not hard. And it's clear that diagonal, clearly, diagonal is contained in VI. Again, because if you have an element of this form, it vanishes on all pairs XX. And then if you have an element in like XY, where Y is not equal to X, you need to find a function which is which vanishes in X and doesn't vanish in Y. So you have a function f such that f of x is non-zero, f of y is 0. This function exists by Hilbert-Nullstellensatz. I mean, you can distinguish between points. Well, it's even from coordinates. It's clear even from coordinates. So you can take some coordinate function which vanishes here, doesn't vanish there, and then you take f times 1 plus minus 1 times f. So f of x, yeah, it doesn't vanish on, and you apply this to the point xy, and this the second term vanishes in y, and the first term doesn't vanish, so this is non-zero. So this gives you converse inclusion as well. Okay. You might need something about nilpotence, but in fact we don't need it, so I will skip it. What I want to say that the corresponding spectra is the same. This is what I will use. Okay, and now we can very easily prove this result about the fiber product. Let's prove it. So this is a definition of fiber product. I will remove it. I suppose you can remember it now. I hope. So now you have an ideal of diagonal in m times m, and then then you have R, which is OX times OY quotient by this ideal. OX times OY over C. This is the product, but then you take quotient by the ideal of diagonal. This is the ring of fiber product by definition. O of x times y over m. But then yeah, but then you also have to show that I is the ideal of diagonal is generated by this is again clear, is generated by this guy. So applying climb 2, we obtain that the spectrum, well, everything is essentially again tautology. So if you have, well, you can just forget what's in there and check that if you have 2 points which are maps to something different, then they don't belong to, well, yeah, so what we use here is sort of crucial, OX times OY over C, quotient by the ideal of diagonal in OM times OM. This is the same as OX times OX times OY over OM. And this follows from these two claims. Because, okay, so what do we need? We need to check. We have to we have to compare to. So this is essentially by definition of tensor product. We have to equate x times r. XR times y is minus x times ry, right? This is what you take the quotient by this when you take tensor product, but this is the same as ideal of the diagonal. And this is, you take x times y and multiply it by the ideal of diagonal. So this is why you obtain this statement. This is what is written there. Okay. I'm sorry if it was slightly confusing, but you should just recheck that later. This is almost, up to, this is just sort of compact form of what we have done before, and the proof is the same, just more abstract. And there's even more abstract version of this. I have 15 minutes, so I would have probably time to do it. You can do it categorically. In fact, in any category, there exists a notion of fiber product. And then this lemma becomes trivial because you have two equivalent categories. You have fiber product in one, you have fiber product in another, and they have to be equal because you can define fiber product categorically. So what is commutative diagram? You probably know. It's just a graph. Like you have x, y, z, t, whatever, and you have like arrows. And commutative means that if you go by arrows in any like direction, any cycle of arrows gives you, if you can go like that or that, this should be the same. Any composition of arrows which takes t to y or any other vertex to any other vertex should give you the same morphism. So this is what is commutative diagram. And also we had initial object of category, we have discussed that. So it's an object of category where you have only one morphism from this object to any other object of this category. It's unique. Something we discussed. Now we can define limits and co-limits of finite diagrams. The good thing is that this is entirely abstract, but then you can have like good mathematics from things like kernels, co-kernels, unions, intersections from these abstract notions. So this is limits and co-limits. So if you have a diagram, you can consider morphisms to this diagram and morphisms from this diagram. It's better to, you don't need actually to work with commutative diagrams, but today we shall, sometimes it's helpful to work with commutative, sometimes not. Just for simplicity, we shall do with commutative. So you have commutative diagram, like triangle or x, y, z. Now you have some t, and you consider maps from this t to all vertices of this diagram, making the whole thing commutative. These are objects of a certain category. And the morphisms in this category is another, like T1, T2. You have an arrow from here, and this is an object of the same category, so you have morphisms from T to all vertices of your diagram. You have a map, and this should be commutative. The whole thing, like lots of arrows, everything should be commutative. And then you define the limit, or co-limit. I always confused with the, yeah. So limit is initial object in there. And co-limit is the same, but with inverse arrows. So co-limit is you invert arrows and replace terminal to initial. So example of limit. Or co-limit, or let's do limit. So you have a diagram of this form. X1 goes to x2, goes to x3, and so on. X4, right? And suppose that they're all inclusions. X0, X minus 1, and so on. Suppose they're all inclusions. And we're interested, this is sets. So this example, this is sets. And you want to have a map, you are interested in maps from T to this. But since this is inclusions, this means that you have a map to intersection of these things, right? If you have a map to intersection of this xi, if they're all inclusions, then this is the same as you have a map to each of them. They're all embedded. So limit of this diagram is intersection. Now, if suppose we're interested in co-limit, this means that we are interested in maps from this from this xi to something. But again, if you have a map from each of xi, they're all embedded. This means that you map to a union. From a union to this, to something. If you have map from x2, from x3, from x4 to some set, this means that you have a map from the union to the same set. So this is direct limit is written like that, and co-limit, inverse limit of xi is union of xi. This is very important. In fact, if we are going to do sheaves, if we'll have time to do sheaves, you cannot avoid doing limits and co-limits. This is like a basis of working with sheaves and many other things. Okay. So the typical example of co-limit is, do you know about periodic numbers? Who knows about periodic numbers? Okay, so then you can have this example, limit inverse of z by Pn is Zp. So periodic numbers are obtained by as inverse limit of finite rings of this form. Okay. Now, but even it makes sense even for finite diagrams. So we're interested in products and co-products. Product. You just take two elements without arrows, x and y, and they take inverse limit. Oh, sorry, direct. Yeah, you take the limit. Limit is the same as inverse limit, and co-limit is direct limit. And co-product is lim. So you have a diagram of two vertices which don't interact. No arrows. So what does it mean, product? This means that you have maps from some z to x and to y. And for each other element which is mapped to x and to y, you have maps from z to this element. This is sort of clear that this is some, I mean, the maps from something to x and to y is the same as maps to a product. And coproduct is, product of x and y, like x multiplied by y in sets is the same as a product, and coproduct is denoted like that. And y is just, for sets, it's just non-intersected union. You just take union, union of two distinct sets. This would give you coproduct. For another application of coproduct, which you probably had, is amalgam. Have you done amalgams of groups? Who knows about amalgam of groups? Not many. About free groups? Okay, so from that, you can easily check from this definition that if you have a coproduct of z, like n, is the same as free group of a number of n generators. Okay, this is product, this coproduct. And you can, if you do that for vector spaces, in fact, the products are the same as coproducts. But if you do that with rings, I'm not sure if we are interested in. Okay, let's do the next slide. It will be about rings. Yeah, so coproduct of rings is tensor product. Why? Okay, so you have ring A, ring B. You are interested, let's suppose, of rings over C, just to be precise. You have a map from X to something, to ring C. You have a map from B to ring C. Then all generators of this gives you a map from A times B to ring C. Just you put A, I mean, this gives you a map from each product of elements of A and B to C. So if I have a pair of maps from A to C, from B to C, this is the same as a map from tensor product to C. This is a one-to-one correspondence. It works. Products and coproducts are the same for category vector spaces. It's just direct sum.
I mean, products for vector spaces are just Cartesian product, and coproduct is tensor product.
No, they are just products, both.
And for rings,
there are different morphisms in category of rings.
the product for rings.
I forgot what it is. Probably Cartesian product. Yeah.
Cartesian product. And
Yeah, and coproduct is tensor product. So the idea is that if you have, okay, you have a map from A to C, from B to C. This means that any generators of A are mapped to C, any generators of B are mapped to C, and this is compatible with their product, so you can like generate by. So A times B is the biggest commutative ring which has the same generators as A and B and the same relations. This is why this is an initial element in this diagram. So if you have any map from, so you have maps from A to A tensor B, from B to A tensor B, and any map from B to C, and A to C is factorized through this map from A and B to a tensor product. This is sort of obvious. Okay, and then this means that you have products in the category of algebraic varieties, which is the same category. I mean, coproduct, we invert arrows, becomes product. Product becomes coproduct. So the product in category of algebraic varieties is precisely tensor product. This explains why we work with this freely. Now let's do with fibered products, and we are done for today, right? Right. So now we can define, again, categorically, the fibered product, and there is also fibered coproduct, whatever it is. Fibered coproduct makes sense for a group because this would be precisely amalgam of groups. Okay, so we're interested in fibered product. So you have A. Questions, comments? This diagram. And we're interested in limits of this diagram, which is called a fibered product. Invert arrows, take colimit, this will be fibered coproduct, or just coproduct. Okay, and now, first, it is sort of clear. In fact, it's sort of clear that in algebraic category, in category of algebraic varieties, product is the same as just product. And fibered product is the same as fibered product. So if you have x and y mapped to M, and you are interested in maps from this diagram to something, this is the same as maps from x and for y, which are compatible on M. But this compatibility on M is precisely that we are interested in, in the map to here because we're taking, yeah. So if you have a map from some z to x and to y, which is compatible on M, this is the same as you have all points of z are mapped to points which are mapped to the same point of z. So the maps from z to this diagram, compatible with the projection to M, is the same as maps to fibered product. So the fibered product in category of topological spaces of algebraic varieties is the same as categorical fibered product. Good. And then the same argument does with the coproduct over some C. I mean, here I didn't take up, I consider them rings over numbers. But if you just consider category rings over C, which means that rings equipped with the map to some other ring, C, like not complex numbers, but just C, and we have M here, or R, it will be all C linear maps to R. And this would give you the product over C, yeah. So you can just check that coproduct in category of rings and product in the category of fibered coproduct in category of rings, fibered product in category of varieties give you what, I mean, one of them gives you tensor product, another gives you a fibered product, and they, by Hilbert Nullstellensatz, these categories are equivalent. So this explains why tensor product is the same as fibered product. Okay. So I'm done. Thank you very much. And next time, I think we shall do some Galois theory. So how many of you know Galois theory already? We need a little bit, not all of it. Just like things like what happens if you take two extensions, field extensions, and you take the tensor product. This is what the part of Galois theory I'm going to use a lot. So see you next time.